In the early 1950s, the skies were no longer safe. The Cold War had entered a phase where speed meant survival. Jet engines were growing faster, radar stronger, and missiles deadlier. The United States Air Force knew that Soviet long-range bombers could soon reach American cities carrying nuclear weapons. And they needed something new, something that could rise from the ground, climb to the edge of space, and destroy the bombers before they struck. The answer was supposed to be a plane faster than any other on Earth, the Republic XF-103. It began in 1951 under a program known as Interceptor Project 1954. The Air Force wanted a supersonic fighter capable of Mach 3, that's over 3,500 kilometers per hour, armed with radar-guided missiles and able to operate at altitudes near 70,000 feet. It was an impossible dream for that era, when most jets could barely reach Mach 1. Republic Aviation, famous for building the rugged P-47 Thunderbolt of World War II, took the challenge. Their engineers, led by Alexander Kartveli, believed they could push the limits of technology using materials never before tried in aviation. The XF-103 would be built almost entirely from titanium, a metal so strong it could withstand the extreme heat of Mach 3 flight, yet so difficult to machine that even the tools to shape it barely existed. Its shape was long and needle-like, with razor-thin wings and a pointed nose that looked more like a rocket than a plane. The design was dominated by a massive intake beneath the cockpit, feeding air to a revolutionary engine system, a combination of a turbojet and a ramjet. At low speeds, the turbojet would power the plane. Once the jet passed Mach 2, the ramjet would take over, using the sheer rush of air at high speed to create thrust without moving parts. In theory, this hybrid system would let the XF-103 cruise comfortably at Mach 3, but the cockpit design was even stranger. The pilot wouldn't climb in from the outside like normal. Instead, the entire seat would lower down from the fuselage on a hydraulic platform. Once inside, he'd sit in a tiny titanium capsule surrounded by armor and heat shielding. If something went wrong, the capsule itself would eject as a self-contained survival pod. Everything about the XF-103 screamed the future, but the future in 1953 wasn't ready. Every system that made the jet possible also made it impossible to build titanium construction, caused endless problems. Welding it required new tools and temperatures that warped the metal. The engines existed only on paper. The ramjet-turbojet hybrid never worked reliably in ground tests. Even the radar system, supposed to guide its missiles automatically, was years away from functioning. By 1955, the program was falling apart under its own ambition. Costs had exploded, schedules slipped, and Republic's engineers were running into physics they simply couldn't beat. At Mach 3, friction would heat the airframe beyond 300 degrees Celsius, enough to melt aluminum and weaken most metals. The titanium could handle it, but not the electronics inside. Still, the Air Force kept the project alive, hoping for a breakthrough. They needed an interceptor that could meet the new threat. Soviet bombers, like the Myasishchov M4 and the Tupolev Tu-95, both capable of reaching American soil. The XF-103 was supposed to meet them high in the stratosphere, fire guided missiles, and destroy them before they ever crossed the ocean. In official renderings, the XF-103 looked unstoppable, a silver spear tearing through the upper atmosphere. But by 1957, another problem emerged. Missiles themselves were replacing manned interceptors. The same technology that inspired the XF-103 made it unnecessary. Ground-launched surface-to-air missiles like the Nike Ajax could already hit targets higher and faster than any jet. And then came the ballistic missile era. Once intercontinental missiles appeared, there was no need for bombers, and no reason for a Mach 3 interceptor to stop them. By 1957, after years of delay, no prototype had ever flown. Not a single XF-103 was completed. The Air Force canceled the project quietly, shifting focus to more practical interceptors like the F-102 and later the F-106. Republic's titanium dream became just another footnote in the Cold War arms race. The remains of the project, a few test components, scale models, and engineering drawings, were locked away. Republic Aviation moved on to other projects, and the XF-103 faded from memory, but in a way it never really died. Its design influenced later high-speed aircraft, especially the SR-71 Blackbird, which finally achieved what the XF-103 had promised: sustained Mach 3 flight at the edge of space. Even the Blackbird's titanium skin traced its lineage back to the lessons learned from the XF-103's failures. The XF-103 wasn't just a failed jet, it was a warning that technology can't leap forward faster than the world around it. In the end, it became a symbol of the 1950s dream of limitless speed, a time when engineers truly believed they could outfly the future. The story of the XF-103 is as much about human ambition as it is about physics. Republic's engineers labored over materials that had never been used in aviation at scale. They created welding techniques for titanium that required temperatures higher than most factories could provide. They experimented with alloys, cutting tools, and adhesives, learning through repeated failure. Every component posed a new problem. Even the fuselage panels, thin for aerodynamic efficiency, had to survive the extreme thermal expansion caused by Mach 3 speeds. An ordinary aluminum plane would twist and buckle. Titanium survived, but joining the panels without introducing stress points was nearly impossible. The cockpit capsule reflected an almost science-fictional approach to pilot safety. At Mach 3, the heat, air pressure, and potential G-forces would crush or burn a normal cockpit. The pilot's survival pod, encased in titanium and equipped with life support, was designed to be ejected as a single unit if needed. This concept foreshadowed future spacecraft ejection designs, though at the time it was revolutionary. The engine system, a hybrid turbojet-ramjet, was the most ambitious element. Turbojets worked at low speeds, ramjets at high speeds. Integrating the two in a single aircraft required precise ducting, and airflow management engineers faced surges, stalling, and unpredictable heat loads. They conducted countless wind tunnel tests, building scale models to refine air intake geometry. Avionics presented another nearly insurmountable challenge. Radar systems capable of tracking high-altitude bombers did not yet exist. Automatic missile guidance was in its infancy. Vacuum tubes and early transistors could not handle the extreme temperatures the aircraft would encounter at Mach 3. Engineers proposed sealed, air-cooled electronics racks and heat shielding, but these solutions added weight and complexity. Every delay compounded the problem. The Air Force pressed for results. Funding grew erratic. The Cold War demanded speed, but the technology was years behind what was needed. Meanwhile, the strategic environment changed. Soviet bombers were advancing, but so were surface-to-air missile systems. Intercontinental ballistic missiles made manned interceptors less crucial. The XF-103's intended role, intercepting nuclear bombers in the upper stratosphere, was becoming obsolete before the first flight could occur. By 1957, no XF-103 had flown. Only parts, prototypes, and models existed. The program was quietly canceled. The Air Force turned to more conventional interceptors like the F-102 and F-106. Yet the XF-103 left a legacy. Lessons in titanium construction, thermal management, and cockpit safety informed later aircraft. The SR-71 Blackbird, which successfully achieved sustained Mach 3 flight, benefited from the research and experience gained during the XF-103 program. In effect, the XF-103's failures helped future aircraft succeed. Engineers who worked on the XF-103 carried their knowledge into other projects. They refined welding methods, structural testing procedures, and material handling techniques. They documented every failure, every partial success, and used those lessons to advance aerospace technology. The XF-103's influence extended beyond aerospace. It informed design thinking in missile programs, early space projects, and even civilian aircraft development. Its ambition demonstrated the cost of reaching too far too soon, but also the benefits of pushing technology boundaries. The human story of the XF-103 is equally important. Designers and engineers worked under immense pressure, in secrecy, and with constant oversight from the Air Force. They faced impossible timelines and technical challenges, yet they innovated in ways that few could have imagined in 1950s America. Even the aircraft's physical remnants tell a story. Models, blueprints, and a few test components survive. They serve as a testament to what could have been and a lesson for what can be achieved with persistence and ingenuity. The XF-103 also became a symbol. It represented the intersection of ambition, technology, and the limits of human capability. It was a reminder that not every idea, no matter how visionary, is achievable within its time. As time passed, the XF-103 faded from public consciousness. It remained known mainly to aviation historians, engineers, and enthusiasts. Yet its story continues to inspire those who study the history of flight and aerospace engineering. It serves as a cautionary tale and an example of how pushing the envelope can lead to innovation, even if the original goal remains unfulfilled. The XF-103 was the fastest plane that never flew. Its titanium frame, hybrid engines, and futuristic cockpit were beyond the capabilities of the era.